I am expecting a lot of questions, Bhargav, today, and also including a lot of people has to ask something, so that I have to take it away and I got to learn something.
I hope, sir.
Yes, yes.
Good evening, one and all. It is my honor and privilege to introduce my guru, Dr. Ranjit Kumar Sahu Garu, to all of you. Dr. Ranjit Kumar Sahu is an assistant professor in the Department of Mechanical Engineering at National Institute of Technology, Surathkal. He earned his BE and MTech degree from NIT Rourkela and completed his PhD at IIT Madras in 2016. With over 17 years of teaching and research experience, his expertise spans in micro and nanomachining, nanomaterial synthesis, precision engineering, additive manufacturing, and advanced joining. Dr. Sahu has published 38 peer reviewed journals, authored 4 books, holds 3 patents, and delivered over 35 invited talks. He has guided several PhD, MTech, and BTech students and received multiple honors, including the Professor M.S. Shanmugan Best Thesis Award from IIT Madras in 2016 and Dr. APJ Abdul Kalam Young Scientist Award in 2018. He has so many laurels in his account. So I am very much enlightened and I am very much thrilled to see Dr. Ranjit Kumar Sahu for this ATAL FDP session. And today, Sir is going to take a session on an innovative approach for production and characterization of unique materials and products, changing landscape in mechanical engineering. Thank you, sir. Thank you for joining us. I request you to take over the session, sir.
Thank you very much, my dear Dr. Bhargav, for briefing my bios case. Am I audible clearly? No?
Yes, sir, you're audible.
Bhargav, am I audible clearly?
Yes, sir. Yes, sir. You're audible, sir.
The PPT is audible. PPT is visual. Visualizing. It is clearly visible.
No, sir. PPT is not shared yet. Please.
Not said, huh?
Yes, not visible.
Okay, again I am sharing. I hope so. Now it is said.
Yes, sir. Yes, sir. Now it is visible.
Okay. Very good evening to one and all. That means whoever attended in this online platform. First of all, I express my heartfelt thanks to Dr. KVJ Bhargav, Dean Research and Development Projects, Deputy Director, DPSR, QIS College of Engineering and Technology. Thanks to Dr. Samir Kumar, the head of the Department Mechanical Engineering QSET, and also to the management of QSET Angol for their invitation and given me an opportunity to deliver a talk in the AICT sponsored ATAL FDP program on the emerging technologies in the field of mechanical engineering. Today I am going to deliver a talk titled An Innovative Corona Discharge Ablation Approach for Production and Characterization of Unique Materials or Products that changes the landscape in mechanical engineering. So in this lecture, I would like to give a spotlight before starting the total lecture hours. As you people knows, there are various advanced manufacturing techniques are available till date. Since decades, those techniques people are adopting and they are carrying out processes to make different products. What we people did, we have imported one technology which is available since decades and modified that technology, built in-house to a certain level of scale and moved into our own innovation. Okay, and these are the outline of this present lecture. First of all, I will give you the glimpse or the overall view of advanced manufacturing. Then we'll switch over to the concept of the arrival of nanotechnology in the field of advanced micromachining, which is under the classification of these advanced manufacturing techniques. In this section, I will discuss the fundamentals of the unique materials, which are so-called the nanoparticles. Then, what are the various techniques available to produce those nanoparticles? Then, I will give a brief exploration of this corona discharge ablation CDA for production of nanoparticles in combination with nanofluids. Then, followed by the characterization studies. Eventually, I would like to focus or spotlight on the application of these nanoparticles, or we can say some unique products, okay, in various engineering systems. These things we'll discuss one by one. So this slide shows the overview of advanced manufacturing. As you people knows, the conventional manufacturing is split off into two parts. One is primary manufacturing processes or techniques. Other one is secondary manufacturing processes or techniques. The primary conventional manufacturing processes are casting, forming, welding, or we can say joining. The secondary conventional manufacturing process is nothing but the machining process. So those conventional manufacturing processes have met the requirements of the industries so many decades. However, to become successful in today's manufacturing industry, the industry has to meet the various demands ranging in the market. In specific, the demands for first one is processing of exotic materials. Exotic means extraordinary materials to achieve a desired shape and size. Second demand is innovative design and manufacture of intricate products at less cost with least human intervention in minimal time and better quality. The third demand is creation or production of miniaturized products. Those miniaturized products we can call the miniaturized features or miniaturized parts or components that can provide more functionality in a given space. The fourth demand is high strength to weight ratio parts. That means we can say, for example, the advanced composites that can exhibit high strength and light in weight. The fifth demand is people want high quality products at less cost, increased productivity with more reduction in wastage of material. So these five demands were putting a lot of pressure on the capabilities of conventional manufacturing processes. So those conventional manufacturing processes will not able to meet those demands. Therefore, industrial researchers have made a continuous effort to advance those conventional manufacturing processes or techniques. Eventually, or we can say ultimately, these advanced manufacturing techniques or processes have emerged as the efficient manufacturing techniques to meet the shortcomings of the conventional manufacturing processes. Okay, that's why these manufacturing techniques comes into picture. These advanced manufacturing processes or techniques. And these advanced manufacturing processes are broadly classified into 7 groups. One is newer casting process. Second one is advanced forming and powder metallurgy processes or techniques. Advanced welding techniques, micro or nano electronic devices fabrication techniques, nano composites manufacturing techniques, additive manufacturing techniques, advanced machining techniques. So under these advanced manufacturing techniques, newer casting, lot of sub techniques are there. Similarly, under this whole techniques, lot of various techniques are available. Okay. So these techniques are available widely in various literatures, in various sources, in various books. So among these techniques, these advanced machining techniques have played a significant role in industries. Okay, so I will focus on these advanced machining techniques. Then now people are focusing on, till today people are working on the additive technology or additive manufacturing technology. Lot of works have been carried out. It is a booming area now related to metal additive manufacturing and metal 3D printing techniques. Then people are following the post processing based on these advanced machining techniques and other kind of techniques, usually to achieve the desired dimension and surface finish. But in this lecture, first of all, I will give you a brief idea about the exploration of one of the advanced machining technique to produce some unique materials like nanoparticles or some nano products, and followed by this is a one kind of subtractive technology, advanced machining techniques. Then we will be switch over to the additive technology. That means people are tilted to working in the area of additive manufacturing followed by the machining process. That means additive followed by subtractive. But I will focus on the subtractive phenomena followed by additive phenomena. Recently, we are exploring this kind of logics. So first of all, you have to know in brief, in a nutshell, what is advanced machining. Advanced machining techniques are those techniques, okay, which has been developed as an efficient and economic alternatives to the conventional machining techniques. Because, for example, when you're going for a precise shaping or machining of some exotic materials, for example, superalloys like cast alloy, wasp alloy, monon metal, then titanium-based alloys, ceramics, carbides, etc. When you're going for precise machining or shaping of those alloys to make a desired shape and size with less cost and high quality, okay, the conventional machining processes are not able to meet that requirement. Therefore, these advanced machining techniques have developed as an efficient technique and surpass these conventional machining techniques. So advanced machining techniques are those techniques which are used to make macro or meso-sized features or products or parts or components by removing the material from the workpiece in the form of debris at macro or meso level, okay, using either mechanical or thermal or chemical and electrochemical energy without any constraint on the size of the workpiece to be machined. Okay, so these advanced machining techniques are capable of machining complex blind shaped cavities, extremely complicated shapes on various engineering materials, deep holes on various engineering materials to a high accuracy and better quality. Okay, so these advanced machining techniques has some various important features. They are non-contact. There is no physical contact between the tool and the workpiece usually. That indicates no contact stress. Hardness, fragileness has no barrier for machining. It can able to produce three-dimensional complex features. Difficult to difficult materials can be machined by using these advanced machining techniques, and it can meet the surface quality requirement. Okay, and these advanced machining techniques has found widespread application in many industrial domains, such as making of small and burr-free drilling holes in turbine blades. They're also making dies, spool valves, keyways for cylinders, etc. But due to the high technology global market in recent times, there is a stringent demand for development of miniaturized products or components like micro electronic mechanical systems, MEMS, nano electronic mechanical systems, NEMS, nanostructured materials, etc. Another demand is requirement of micron or submicron features like micro holes, micro channels, okay, micro groups, micro slots on various engineering materials. The another demand is that means nano level surface finished products. So those demands will result in various benefits. That means they can save the material, saves the power, then saves the space, ease of transportation. They can make the system simple, compact, and light. They can permit more functionality in a given space. They can increase the system's overall efficiency. Okay, so these demands are not able to meet by this advanced machining at macro or meso level. So to meet those demands, this advanced machining at micro or nano level, okay, have become increasingly important and meet those demands. So these advanced machining techniques at micro or nano level, we can call in other way advanced micro machining or nano machining. So advanced micro machining techniques are those techniques which are used to make or create or product or produce features that is micron size or submicron size or nano features or parts or components or products, okay, by removing the material from the raw workpiece at micro or nano level using precisely controlled these energy sources. And those advanced micro machining processes involves low input energy, that means in the terms of microjoule, then low range of input parameters, micron size tool, okay. So those low unit removal of material, those advanced micro machining has various features. So these advanced micro machining processes are broadly classified in this table. You see in this table, these are the broad classification of these advanced micro machining techniques or processes. So based on the mechanical energy, the techniques include ultrasonic micro machining, abrasive jet micro machining, water jet micro machining, abrasive water jet micro machining, wherein the principle of material removal is mechanical erosion of workpiece materials using abrasive particles. Similarly, based on thermal energy, these techniques include corona discharge micromachining, or you can say spark micromachining, or corona discharge ablation machining, electron beam micromachining, laser beam micromachining, ion beam micromachining, where the mechanism or the principle of material removal is melting and evaporation of workpiece material. Further, based on chemical and electrochemical energy, the techniques include chemical micromachining, electrochemical micromachining, where the material removal principle is corrosive reaction and ionic displacement respectively. In recent times, this advanced micromachining in hybrid form has been adopted by the researchers, okay, to meet the various requirements in the industry. And this hybrid micromachining processes combines the various energy sources and they are integrated in a single machining platform. So those processes or techniques include electrochemical spark micromachining, which is based on electrochemical and thermal energy, wherein the mechanism of material removal is melting and evaporation followed by chemical etching. Similarly, chemomechanical polishing and electrolytic in-process dressing. These are the hybrid micromachining techniques processes wherein the principle of material removal for the CMP is chemical reaction and mechanical abrasion, and for CLID, electrolytic reaction and grinding action respectively. Okay. So these advanced micromachining techniques are found to be used in various promising industrial domains. For example, machining of micro features like micro holes on fuel injection automotive nozzles. I'm telling you for examples. Then filters. These micro holes are made in filters which are used for food processing, textile industries, and other applications. These micro holes are used in for cooling holes in turbine blades, in spinners for synthetic fibers, in needles, catheters, and other medical device equipments. Moreover, microchannels, these techniques are used for machining of microchannels in nuclear reactors, then MEMS devices, microfluidic devices, etc. Various applications are there. It are here also mentioned. I need not to read it one by one. Okay. So those features which are obtained, the main list there is the how they are obtaining by removing the material in the form of chips or debris. But recently, researchers have paid some attention on the unwanted materials, that is debris, okay, where they are going, how it looks, how it behaves. So recently it became a challenge for the researchers to concentrate on those debris, to collect those debris, to test those debris and reveal the structure of debris and their applications, possible applications as nanomaterials in the field of nanotechnology. Accordingly, the concept of the nanotechnology in the field of this advanced micromachining arrived or advented. So now I'll switch over to the next slide. How that means the concept of nanotechnology has been advented in the field of advanced micromachining. Okay. So the next slide shows that these fundamentals of nanoparticles. I will tell you in a very brief way. This nanotechnology research, that means we can say the research on nanotechnology is evolving and expanding very rapidly in this century. So nanotechnology simply deals with materials or structures at nano level. So different people have different opinion about nanotechnology. What it is exactly? So nanotechnology is nothing but, some people says, the study of microstructure of materials using a microscope is considered as nanotechnology. In some other country, people says the study of the growth of thin films is considered as nanotechnology. In some other parts of the country, people says the drug delivery systems, the labs on chips, MEMS devices, NEMS devices are considered nanotechnology. However, in USA, people says the materials and structures and systems whose structures and components are in nano level scale, they are considered as nanotechnology. But in general, the nanotechnology is defined as the production, characterization, and application of nanomaterials or nanostructured materials. So those nanomaterials or nanostructured materials are those materials which are having at least one dimension in nanometer scale, that means less than 100 nanometer. Those nanostructured materials, based on the dimension, they are classified into three forms. One is zero-dimensional nanomaterial, one-dimensional nanomaterial, two-dimensional nanomaterial. So zero-dimensional nanomaterial are those materials whose all the dimensions are in nanometer scale, that means less than 100 nanometer. For example, nanoparticles, okay? Then we can say quantum dots. These nanoparticles may be spherical shaped nanoparticles, polyhedral shaped nanoparticles, cubical shaped nanoparticles, triangular shaped nanoparticles, pillar type nanoparticles. There are various shaped of nanoparticles are there. Similarly, one-dimensional nanomaterials are those materials whose one dimension is in outside the nanometer scale. For example, you can say nanotubes, nanorods, nanowires, nanofibers, etc. Two-dimensional nanomaterials are those materials whose two dimensions are outside the nanometer scale. For example, we can say nano layers, then graphene, then thin films. Okay, these are the examples of two-dimensional, or you can say nano coatings. They are the examples of two-dimensional nanomaterials. So among those zero-dimensional, one-dimensional, two-dimensional nanostructured materials and nanomaterials, the field of nanoparticle technology has drawn a lot of attention among the researchers and have grown and is growing very fast in the current scenario. Okay, these nanoparticles are microscopic particles whose size typically lies in the range of 1 to 100 nanometer. Okay, and these nanoparticles effectively bridges the gap between the molecules and the bulk material. These nanoparticles play a significant role in scientific, medical, and industrial applications due to their size dependent, due to their enhanced size dependent characteristics. Enhanced size dependent characteristics as compared to its bulk form. So their uniqueness arises due to their large surface area to volume ratio, indicating a large fraction of atoms present on the particle surface that are chemically unsaturated. Therefore, this table shows, according to Hosokawa et al. In the year 2012, it shows that how a bulk material and scaling down into a particle form, how it that means behaves in a very extraordinary way based on the number of particles present on the particle surface over its whole volume. You see, when the size of the particle is 20,000 nanometer, you see the percentage of atoms present on the surface over its whole volume is 0.006 percentage. When this particle is scaled down to 2 nanometer, you see almost 50% of atoms present on the particle surface as compared to its whole volume. So this particle can behave in a very extraordinary way because the atoms which are present on the particle surface, okay, they will have a different environment as compared to its whole volume or interior atoms. The atoms present on the particle surface, they will have a different energy state of distribution as compared to the atoms in the interior of the particle. So those atoms which are present on the surface, they will have a high energy state of distribution as compared to its whole, as compared to the interior atoms. So the difference in the energy of the distribution, okay, that creates a high distribution. That means we can say the difference is leads to that there will be a high energy distribution at the particle surface of atoms rather than its interior. So this difference we can call as a high surface free energy, that means surface free energy. And due to this high surface free energy, the particle size of 2 nanometer, which is lowest from this one, from here to here, that can exhibit extraordinary behavior. That means you can say those particles can exhibit novel properties like physical properties, novel mechanical, electrical, thermal, catalytic, antibacterial, optical properties or characteristics. Okay, why this? They're exhibiting the extraordinary properties and novel properties because of the large surface area to volume ratio, or you can say because of the high surface free energy. Okay, this is about the fundamental about these nanoparticles. Moreover, in recent times, there is a great attraction towards nanofluids, which are proven to be much superior than the base fluids. So these nanofluids are nothing but they are the dispersion, they are nothing but colloidal suspensions or colloidal dispersions, wherein the nanoparticles are dispersed in a base fluid. Those base fluids it can be include either water generally or organic liquids like ethylene glycol, oils, etc. Okay. So due to the presence of these nanoparticles in the base fluid, those nanofluids can exhibit excellent thermal, rheological, and tribological properties as compared to the base fluids. Okay. So accordingly, the nanoparticles without any colloid or with colloid, we can say in combination with nanofluid, can be they are used in various interdisciplinary emerging applications. Indicatively, such applications include they are used in automobile radiator to cool the engines. So they makes the radiator lighter and what we can say lighter and smaller. So as a result, the engine radiator becomes small and light in weight, and the drag force will be less, and the fuel consumption will be less, then the engine efficiency will be improved. Those particles are used in MEMS devices. They can pass through tiny passages in the MEMS devices to cool these devices, electronic devices. They are used in heat exchangers. They are used as a catalyst in lithium ion batteries. That means they can able to increase or decrease they can able to charge at a faster rate and discharge at a faster rate. They can increase the service life of the battery. They are used as a ingredient in rocket propellants. Okay, so that can, when they're used in rocket propellants, they can increase the energy release. They can have a faster energy release due to the high enthalpy of combustion, and as a result, that can augment the rocket more faster and also reduce the smoke which is coming out from the rocket while it is augmenting. They are used in explosives to have a higher, a faster energy release and have a, that means high detonation capacity. They are used in biomedical applications, for example, in drug delivery applications to kill the cancer cells and highly deadly viruses. They are used in packaging materials to protect the food from bacteria. They are using automobile bodies, outside bodies, okay, so that they can be used as a self-healing material when it is subjected to some external loading condition. They're used in automobile dampers in the form of a magnetoroyological fluid, and various applications are there. So, owing to the many potential applications of these nanoparticles in combination with nanofluids, so it becomes a great interest for the researchers to concentrate on these nanoparticles, that means to produce these nanoparticles. That's why there are various techniques which can are developed to produce the nanoparticles. So I will show you the next slide. You see, this slide shows the broad classification of the production of nanoparticles. Broad classification of the techniques or the processes which are used for production of nanoparticles. So before in hand, these nanoparticles are produced by two approaches. That basically there are two approaches to produce nanoparticles. One is top-down approach, other one is bottom-up approach. So in the top-down approach, the nanoparticles are produced by mechanical crushing of the bulk metal into nanocrystallites. In the bottom-up approach, the nanoparticles are produced by from the atomic or molecular level, which is combined either by atom, or molecule by molecule, or cluster by cluster. So under this top-down approach, the mechanical assisted techniques include ball milling, lithography, some other techniques also available. Under the thermal assisted techniques, lot of techniques are available. Under the chemical assisted techniques, lot of techniques are available. Okay. In addition to that, there are two routes to formulate those nanoparticles dispersed in a base fluid called nanofluid. One is a two-step route, another one-step route. So in a two-step route, nanoparticles are first produced, or you can say it is commercially available, and then dispersed in the base fluids. Whereas in one-step route, nanoparticles are directly produced in the base fluid. So this one-step route or single-step route can offer various benefits as compared to the two-step route. What are the benefits? That means it avoids the process of drying, storage, transportation, and redispersion of nanoparticles. So as a result, the production cost will be reduced. And also in a single-step technology or single-step route or one-step route, the nanoparticles which are produced directly in the base fluid, if those materials which are of high conductivity and more prone to oxidation, it can prevent the formation of the oxide film on the particle surface. This is one of the important leads for this one-step route. Okay, so there are wide varieties of techniques which have been developed by the researchers to produce nanoparticles both in colloid or without colloidal form, that means nanofluids form. Okay, of desired shape and size, so that it can be used in various potential applications. But it has been found that some of these methods are difficult to control the size and distribution and their subsequent agglomeration. And some other methods, they can exhibit high production, that means low production, that means high production cost. Therefore, there is a recognized need to have a technique that could be simple, compact, versatile, and cost effective. and can produce the nanoparticles in combination with nanofluids in a single step technique. Okay. So what happened recently? This corona discharge ablation technique, or you can say spark discharge micromachining technique, is recently explored to produce the nanoparticles. Okay, and this corona discharge ablation is nothing but it is one of the advanced micromachining technique which is based on the corona discharge or the electrical discharge in the form of a light, in a glow of light. Sudden discharge of electron takes place. Okay, based on the corona discharge or the electrical discharge between the two electrodes. One electrode we are taking as a tool, as a cathode usually, and workpiece anode. Okay, both are separated by a small gap and surrounded by a dielectric fluid. And this technique is used for machining of micro features like micro holes, micro channels, and various engineering materials. Those micro features are obtained by removing tiny bit of materials in the form of debris through melting and evaporation phenomena. Okay, using repetitive spark discharges or electrical discharges or corona discharges. Okay, so some of the debris are evaporated, and some of the debris are dispersed in the dielectric fluid. It is quite interesting to note that the debris which are dispersed in the dielectric fluid are of quite small size, and recently the researchers have explored these debris and their possible application as nanoparticles in various promising fields. So I will show you the experimentation part, then some illustration part. I will show you one by one. Bhargav, am I audible clearly?
Yes, sir.
Bhargav?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, it is clearly audible, right?
Yeah, it's clearly audible, sir.
Okay, thank you. Then we are switching over to the exploration of the corona discharge ablation or production of nanoparticles. See, this is the experimentation part. This figure shows the block diagram of the indigenously developed corona discharge ablation setup, and this is the photography view of this experimental setup. And this figure shows the close-up view of the ultrasonicator and tool workpiece system. And this is the piezo actuator. See, this setup consists of a tool which is connected to the negative terminal of the DC power supply, workpiece connected to the positive terminal of the DC power supply. This can be called as a cathode, this can be called as an anode. These two electrodes are separated by a small gap known as inter-electrode gap or spark gap or corona discharge gap, and they are immersed in an dielectric medium which is contained in an ultrasonicator. Okay, and this ultrasonicator is used to produce ultrasonic vibration at a certain frequency to avoid agglomeration of the particles and achieve uniform dispersion of the particles or debris which has been produced in this dielectric fluid or dielectric medium. This ultrasonicator can also aid in the removal of the debris from the spark gap region efficiently and avoid the accumulation of debris in the spark gap. This will result in stable spark discharges or corona discharges and increased machining efficiency. In this setup, a piezo actuator was used. This is a piezo actuator figure. This piezo actuator used to feed the tool towards the workpiece, to maintain a constant gap between the electrodes during machining process. So the piezo actuator consists of two piezo stacks arranged in series. So each piezo stack consists of 0.1 mm thickness, consists of 196 piezo wafers. Each piezo stack consists of 196 piezo wafers of 0.1 mm thickness and 25 mm cross sectional area. These two piezo stacks are housed inside a flexural link. This is a flexural link. The upward and downward movement of this piezo actuator is caused by this flexural link. Okay. So the maximum displacement of this actuator, APA 400M, is found to be 400 micrometer. That means plus or minus 200 micrometer during the processing time at a amplified voltage of 154. In this setup, a pulse generation and control unit, or we can say pulse generation circuit. Pulse generation and control circuit is developed, and this circuit nothing but it is a MOSFET based pulse width modulated pulse generation control circuit that provides rectangular pulses, okay, at a frequency of 1 kilohertz to 5 kilohertz and duty cycle of 5% 50% to the electrodes. And this pulse generation and control unit or circuit consists of a pulse width modulator that can provide different shapes of rectangular pulses, different shapes of pulse voltage waveforms to the electrodes. Here, the frequency and the duty cycle of the pulse discharge are controlled by adjusting the values of resistance and capacitance connected to the potentiometers. Okay, we are using the potentiometers, then we can able to adjust. And one of the important, the that means we can say the innovative thing in this circuit is nothing but the pulse duration can be set at any point of time during machining by changing the frequency and duty cycle, depends on the machining conditions required. In this setup, an oscilloscope is used which can capture and monitor the voltage waveform during machining process. Okay. So what is happening in the next slide, I will show you the close-up view here. You see, using the adjustable knob, this is the adjustable knob initially we have fabricated. Using this adjustable knob, the tool is moved towards the workpiece until it reaches the required spark gap. Due to the high potential gradient across the electrodes, what is happening? The dielectric breakdown occurs. That indicates when the voltage builds up to a predetermined value, the electrons from the tool will break loose and starts to move towards the workpiece, that is towards the anode. So during their travel within the inter-electrode gap, there is a dielectric medium which contains the neutral atoms or molecules. So these electrons which are emitted from the tool, they start to collide with the neutral atoms or neutral molecules of the dielectric fluid, and those atoms or molecules will get ionized, so that what is happening, these electrons starts to move towards the workpiece, and simultaneously the positive ions or holes moves towards the tool or cathode. This is nothing but the avalanche motion of electrons. Okay, and all of a sudden what is happening, a plasma channel will be formed, the whole column will becomes ionized. Okay, this plasma channel will enable the spark discharge. This is the plasma channel. This plasma channel will enable the spark discharge to take place. Due to the spark, a localized intense heat is produced, which increases the temperature of the workpiece equal to its melting and vaporization temperature. As a result, the material will be removed in the form of debris, and that will be dispersed in the dielectric medium. Okay, so this is the process, and those debris which are dispersed in the dielectric medium, we can call it as a colloidal debris, and those colloidal debris will be carried out for successive characterized studies. Oh, then this figure shows the close-up view of the transition of metallic vapor to formation of particles. You see, when the metallic vapor is ejected out from this molten pool, those starts to condense in the low temperature region, the dielectric medium, and they starts to nucleate in different orientations. Once the nucleation starts, then this followed by the growth of this particle, growth of this nuclei in different orientations. Then this particle growth can be controlled by using either the physics behind the coalescence and collision rates. When the coalescence rate is less than the collision rate, we can able to obtain the spherical sized particles. When it is more than that one, at high particle concentration, then the agglomeration starts to take place. This is the very basic phenomena we have to understand. Hello, what happened? Any question? Hello. Bhargav, somebody asked question, right?
No, sir. No, sir.
Okay. Then, in this way, the mechanism of the formation of these debris, which are displayed in the dielectric medium, will be collected in the glass vials or some test tubes, and you are carrying out for different characterizing studies. For example, this is the work we have carried out so many years before. this preparation of copper nanoparticles or production of copper nanoparticles. One illustration I'm showing you, first illustration. You see here, these are the experimental parameters which has been taken for production of copper nanoparticles. And this is the characteristic of piezo actuator. This is the voltage waveform which has been obtained in the kept in the oscilloscope. And these are the carbon coated copper grids which are placed in this filter paper. And once the colloidal debris is collected in the glass vials or test tubes, we have started for dribbling those colloids on the surface of this carbon coated copper grids and allowed for drying for 2 to 3 hours. Then the dried sample is taken for some certain microscopical and other characterization studies. First illustration is the characterization of copper nanoparticles. You see, this figure shows the transmission electron microscope images of the copper particles. We have taken one of the workpiece as a copper and we have produced the particles of copper in the pure DI water. These particles are almost spherical in shape, and the size of the particles lies in the range of 600 to up to 1100 nanometer, with a mean size of 880 nanometer. We have calculated for that one. So those such large size particles are well-defined single particles, and they are obtained due to the agglomeration of the particles, the agglomeration of the particles at very fine level, okay, which is resulted from the combination of the van der Waals forces of attraction and the Brownian motion during condensation and nucleation of copper metallic vapors during that time. This image shows a copper particle, that means a submicron size copper particle with a dense structure at the periphery. This may be attributed to the collision of nucleated nanoparticles to form a larger sizes. And this figure shows the copper particles with no dense structure at the periphery. Here more dense, no dense. Why? Because this is the collision. This is due to the clustering of primary copper nanoparticles. This phenomenon is obtained. And to verify these particles with the presence of any kind of impurities in the sample, so we have carried out the energy dispersive analysis X-ray study and also selected area electron diffraction SAED study. So this EDEX pattern shows that distinct elemental peaks of copper particle due to the transition of electrons to the K and L cells, to the L and K cells in copper atoms. This indicates the presence of copper particles in the sample in pure DI water. As copper contains high atomic density crystallographic facets, here different peaks of copper, example 4 peaks of copper are observed at different crystal facets. Moreover, here oxides formation also negligible, and so there is no kind of impurities present in this sample. Moreover, we have carried out selected area electron diffraction pattern to identify the crystal structure of these particles, whether it is oxidized or not. Okay, so you see here, this is the diffraction rings. So this shows a sequence of electron spots, each spot related to the specified diffraction condition of the crystal structure. This ring shows a clear diffraction rings. The diameter from the center to each concentric ring was measured. The first ring diameter yields a lattice spacing, D spacing of 0.21 nanometer. That perfectly matches with the FCC crystalline lattice distance of 0.20 nanometer for this 111 plane, HKL plane. Similarly, the lattice spacing for the next two rings found to be 0.128 nanometer, 1.18 nanometer for 200 plane and 0.126 nanometer for 220 plane. This also perfectly matched with the FCC crystalline lattice distance of 0.18 and 0.128 for 200 and 220 planes respectively, as per the JPDCS rule, JPDCS database. Okay. Then after that, what happened? From this EDEX and the SAT pattern, it has been verified that the particles which are obtained, the copper particles, are of pure crystalline in nature, and there is no such kind of impurities present in the sample. But it has been observed that those particles which are obtained are of submicron size rather than nano sizes. Even though ultrasonic vibration is provided to avoid the agglomeration of debris, but still large size particles are obtained. This indicates that the ultrasonication was not so much effective to prevent the agglomeration. Also, by visual inspection, okay, after 4 hours of the collection of this colloidal debris, it has been observed that the dispersion stability of the copper particles in pure DI water found to be poor. That means we can say the sedimentation or settling of copper particles in the DI water takes place in a very faster way. That is, after 4 hours of the collection, the particles has been settled down. So to overcome this problem, what happened? That means as per the surface chemistry of this copper particle and DI water, some polymeric stabilizers are adopted or used in this study. So one stabilizer we have used, that is polyvinyl alcohol PVA, and this polyvinyl alcohol, okay, that means it can study the effect of interaction between the nucleated particles as per the surface chemistry. Okay, and these polyvinyl alcohol PVA can exhibit exemplary characteristics, that is non-ionic, water soluble. It has strong film forming quality and wetting effect. Okay. So when this polyvinyl alcohol is added to the DI water at a concentration of 1 weight per volume percentage, then the experiments were conducted under similar input conditions. Then this is the time image of the copper particles which has been dispersed in this PVA solution. So these particles, the each bright crystalline particles we shows here in this image, they represents the copper nanoparticles of size lies in the range of 2 to 10 nanometer with a mean size of 7 nanometer. So here the particle size distribution follows log normal distribution, and this is the index pattern for these particles dispersed in this solution. Here what happened, that means some kind of small impurities iron has been observed. In addition to carbon and oxygen has been picked up due to this PVA. Then moreover, this SAD pattern also has been carried out with respect to this sample. So this SAD pattern shows the blood rings rather than the clear diffraction rings. This is due to the presence of the amorphous nature of the stabilizer on the copper particles. Even though the lattice spacing for each plane is perfectly matched with the FCC crystalline lattice distance of copper. Okay, but you see here the mechanism of the reducing the interaction between the particles. That means you can say avoiding the agglomeration of the particles is shown in this figure. You see, when the nano, for example, I took these two nanoparticles. When the nanoparticles are produced in the base fluid, for example, dielectric fluid, the dissolved stabilizer molecules are arranged in such a manner, okay, arranged such a manner because of their chemical affinity, okay, and because of their amphiphilic nature, that their hydrocarbon chain, this is the hydrocarbon chain, this is the polar head group. The hydrocarbon chain is in contact with the surface of the particle due to the chemical affinity, and the polar head group is oriented towards the liquid medium. So in this way, these stabilizer molecules forms a thin layer on the surface of the particle, here surface particle. So this polymeric cell will have a strong barrier to prevent the close contact between the particles. In this way, the particles of individual sizes in the range of 2 to 10 nanometer, mean size 7 nanometer, obtained in this sample. However, after 36 hours of the collection of this sample after experiment, it is found that still sedimentation of particles takes place. It is after 4 hours only in DI water, after 36 hours by visual inspection. Okay, then this is what is the problem behind it here? Due to the high concentration of that means hydroxyl molecules in the PVA, okay, that can able to detach after some period of time. That means due to the high concentration of hydroxyl groups in PVA molecules, so they do not adsorb extensively on the particle surface. Then it starts to settle down after some period of time. To overcome this problem, That means we have carried out various experiments to identify the stabilizer as well as the surface chemistry. Finally, we have adopted polyethylene glycol is one more stabilizer. By using this stabilizer, the size of the particles lies in the range of 4 to 10 nanometer with mean size of 6 nanometer, and excellent dispersion stability of the copper particles dispersed in a solution has been found. Even though after 2 months there is no settling of particles takes place, after 6 months also no settling takes place, excellent dispersion stability has been obtained. This is about the copper particles which has been produced of the size of almost 6 nanometer mean size, and that can be used in certain industrial applications. For example, I will show you one industrial application here. Application of these copper particles, or we can say the colloidal copper nanoparticles in thermal management system. You see, my dear audience, this is the schematic diagram of the developed thermal management setup for heat transfer study, and this is the photographic view. So this setup consists of a cylindrical beaker, stainless steel cylindrical beaker, wherein the fluid medium will be poured inside the beaker. An external heater arrangement has been made. This is a heat exchanger of 3 meter length. Okay, this is a brass valve, and this is one small beaker where the fluid flowing through the heat exchanger pipe and collecting here. And at various points, the thermocouples are connected. And this arrangement is coupled with some solid state relay and temperature controller and interface with data logger, okay, with the computer, with the software. First of all, we have passed the DI water heated to a certain temperature, 40 degrees Celsius. The brass valve is opened and passed through the heat exchanger, and the temperature at various locations are recorded. Similarly, when you use these copper nanoparticles which are produced in PEG solution, heated at the same temperature and passed through the heat exchanger and collected in the glass beaker. You see, from this figure it can be found that the temperature, that the heat transfer capability of this copper nanoparticle dispersed in PEG solution is found to be more effective as compared to the DI water. So these colloidal copper nanoparticles can be used in automobile engines that can substitute the presently used ethylene glycol or the ordinary fluids. Okay, so it can have a high heat transfer capability in the heat. That means, for example, in automobile radiator, which can make the radiator lighter and cooler, the same kind of lighter, and we can say that means simple lighter, light that means also smaller, that can exhibit, that means less fuel consumption and increase the efficiency of the engine. And this has been also proved with respect to this thermal conductivity values. And this thermal conductivity of these copper particles has been measured by using a thermal conductivity probe. It has been found that you see the thermal conductivity of the copper particles dispersed in DI water, EBS solution, PEG solution found to be more as compared to the DI water. And within this, the copper particles dispersed in PEG solution found to 15% more as compared to the DI water, due to the presence of the less size of copper particles, the mean size of 6 nanometer. Then these are the various promising applications of copper nanoparticles in various tribological systems. They are used in the engine system, in drawing dies, in cutting tools, in cogging process. That means in what we can say in various cogging processes, in roll forging nowadays. An illustration 2 is, that means preparation or production of smart nanoparticles. For example, I will show you the nitinol nanoparticles. In recent times, the smart nanoparticles have gained a significant research and market attention across the globe. So as you know, in the bulk form, the smart materials can behave in a very extraordinary way based on the changing the stimulating conditions or environmental conditions. So they can exhibit various extraordinary properties. Okay. So similarly, what happened? It becomes a challenge for us in the that means like recent days. We started to focus on these smart nanoparticles. We took one of the smart material, nothing but which exhibit the set memory alloyed particles, for example, nitinol nanoparticles. So these nanoparticles we have produced by developing one setup. Recently, my students have been carried out. You see, this is the one small setup. It is very cost effective. Under the vacuum atmosphere, we have that means we have developed this complete setup, and we made three-axis arrangement for this setup. Then this is the setup we have fabricated recently, and the control system, the experimental parameters we have took here, and we conducted the experiment. You see the experimental part. It is very cost effective. We have changed that means the whole circuit part, making a very cost effective manner. Then we have that means we have reduced the power supply effect, wherein we are purchasing very high cost power supply reduced to a low cost power supply of high quality. You see the how the spark occurs continuously. Continuous feedback is going on.
बीटेक स्टूडेंट ने किया था। बीटेक मतलब कि बीटेक खत्म होने के बाद खुद के स्टूडेंट है, स्टूडेंट है वो नहीं, बीटेक खत्म खुद के स्टूडेंट ने स्टार्ट किया था। इशू था था भी था, कंप्लेन किया था वो बीटेक स्टूडेंट। हाँ किलोमीटर का 3 डायरेक्ट बोल दिया। दो गाइड को हरासमेंट कर रहा है। वो रात भर वहाँ पर करता था। तो क्या हुआ था कि
So this is the complete now recently developed the lab from our group, and they are working. And currently our Devendra Kamble, he joined as an assistant professor on contract basis in College of Engineering Pune, and our Deepak got selected in Ola at a cost of that means his CTC is 20 lakhs per annum, and these are all my BTech students. He joined in Bharat Petroleum in the
बीटेक खत्म होने के बाद
material sector, and other students have joined in various organizations now.
हाँ बीटेक खत्म होने के बाद
You see the results here. This result shows the field emission scanning electron microscope images of nitinol particles produced in DI water. We found the size of the particles 100 to 150 nanometer, mean size of 133 nanometer. The ATS pattern shows the nitinol nanoparticles with
मतलब 100 साल
negligible impurities at a frequency of 5 kilohertz and 50% duty cycle. And the data potential results also shows that the dispersion stability is a little bit poor here.
फिर
Okay, then what happened? We have just changed the duty cycles. During the duty cycles, the duty cycle is reached to 30%, the mean size reduced to 35 nanometer. That indicates what? When the pulse duration is very small, then we can able to remove the material at a very low scale. That means the low unit removal of material takes place, and we are able to achieve 35 nanometer in the vacuum atmosphere, and also with a cold environment at the temperature of 4 to 5 degrees Celsius. So now we are working in this area, the nitinol nanoparticles. The main challenging here is how these nitinol particles have a set memory effect in a particular application.
तुरंत मना कर दिया।
So now my students have simulated that environment, how it can be act as a set memory effect based on the austenite and martensite phase structure changes, based on the changing the environment. So when a bulk material is there, just you heat it or bend it and put in a hot environment, again comes back to the original position. That is the bulk form. But in a
50% खत्म किया।
but the same bulk form when it's reduced to a nano level, how we can prove it? That means it is a shared memory effect. It is quite challenging. Till now, people have not explored across the world. So we are considered that the simulation environment has been completed. Now, the practical setups, that means people are already developed. So I'm not able to see those things because we are patentable work. So these things you are doing this currently. And the spotlight and application of this prepared nanofluid for additive nano manufacturing, you see, very simple. And this is one set of recently people have developed. In SRM University, we have developed, and also in our NITK recently we have developed by my student, by my MTech student. And this is the concept what why you have developed here. You see here already people. That means this is a subtractive technology where you are producing the nanoparticles. So why not these colloidal nanoparticles can be used in a setting kind of, that means innovative system. So these colloids will be accelerated through a nozzle and one substrate will be preheated so that we can use these colloids and added on this substrate in a very fantastic meticulous way so that we can have an additive phenomena at nano level. That's why this is a very, very recent work. That means I'm telling you, people have not explored practically. You can go through various literatures that people are going to make some kind of nano additive manufacturing products. So now one of my Pranit and Umesh, they have developed along with one MTech student, and they started for these nozzles how to accelerate and how to make the print so that they can able to pour on the substrate. The spreading will not be get affected. These things they are studying now. This is a very new concept, and these things, that means you see how they have. Hello, am I audible, Bhargav?
Yes, sir. Yes, sir. You're
This
audible.
is, I think so. Yeah, no problem. See, that means we can able to make it layer by layer, one dispensation over another dispensation. By this, what is happening? We are going to able to make a nanoscale patterning in the printing direction. So this nanoscale patterning is used in currently in high-end electronic devices, or we can say in semiconductor devices. Okay, they can able to make nanorods, photonic metamaterials, energy harvesting, lithium-ion batteries, nano antennas. People are focusing nowadays. This is reviewed. Now, practically, people are focusing in this area. And one of my students is also working, currently PhD student is working in the area of metamaterials. That is very new kind of concept he is working. So the authors like to acknowledge the SERV DST for providing the core research grant to carry out the research work related to these intelligent nanoparticles. So we've carried out more number of works, the extensive works. I'm not able to show because now we are in a patentable position for that one. And this is the patent which has been now recently, this patent also we filed and is under examination now. Thank you. Bhargav?
Sir, very nice presentation, sir.
Bhargav, that means time is I became very tired today because for the last 3-4 days I'm totally tired.
Yes,
And
sir. Yes,
doing 2-3 classes every day, then this SRC work, some other kind of my PhD students work, then my BTech students, special projects, Viva.
no, it is all visible in your presentation, sir. The number of different types of setups that have been developed in your lab.
Now they developed Bhargav. One time if you are coming, you can able to see how my lab has been developed now by bringing that project. And
Definitely.
people what they did now, they went for mathematical modeling of this smart nanomaterial.
Yes.
And now the main important physics is in the bulk form already everybody working. But in nano form, the smart nature, how it behaves at atomic level, molecular level. That application oriented proof is required now.
Yes, sir. Yes.
Why I am telling you application? For example, if you are taking the smart nanomaterial and using in some kind of emulsion or paints, and those paints, if they are coating in the automobile body, suppose let us say some kind of mechanical scratch happen. Okay, when there is a mechanical scratch happen, so automatically it has to self-heal. Like one scratch happened in our body, after some time it self-heals. Am I right or not?
Yes, sir.
So this kind of phenomena we are studying at application level at the atomic or molecular physics.
Okay. There are okay.
So
I'll ask.
I just expect some questions, Bhargav, now.
Yeah, that's right, sir. Dear participants,
I will be happy.
you are free to ask questions.
Yeah, I am free to.
Sir is also free to answer it.
Yeah, yeah.
Yes, sir. We'll start with Dr. Samir. He wants to ask.
Yes, no problem. Please.
Sir, can we have any fabrication of nano hybrid particles, sir? Like copper and ZNO, like that
Yeah,
kind
yeah.
of.
Actually, already we have worked and it has been patented also. My first patent related to the generation of the nanoparticles of elemental type and hybrid type. Elemental type, already I shown you one example. Hybrid type is nothing but, first of all, that means we have produced copper and silver. Okay, so and also we produce now. My another student is working in the area of, like, in fuel cells. People are using that we can say, you know that on the platinum, some carbon material or some we can say some kind of carbon nanotubes they can seat, forming a seat on the platinum. Are you getting my point? Hello.
Yes, sir. Yes, yes.
Yeah, then what happened? People are working now. We have worked in the area of that means silver and copper. How they found a hybrid form. These also we worked out. Hybrid nanoparticles.
Actually, I worked on nickel and Al2O3 particles through
Nickel and Al2O3. Okay. Alumina. Okay. Huh.
through electrolysis plating technique, sir.
Electrolysis plating. Okay. That means you have that, like, similar to, like, we can say that electroplating technique, no? But
Yes,
it
sir.
is electroless, but like electroplating phenomena.
Yes, yes.
Okay.
So,
Huh.
in which the Al2O3 particles will act as the core and the nickel as the coating material.
Yeah, our like that only that we took the silver as a core and the copper as a core, and silver is like a, we can say, cell, the core cell structure.
Oh.
Yeah, but but my question is the nickel and alumina. We have to study the chemistry behind it, how it will be bonded, or how it will be seated on its periphery. That is very important.
Yes, yes, sir.
Because simply we are producing and we don't know the physics inside. So all of a sudden, when you are going for some microscopical images, then you will see, okay, this particle becomes a core, and on this cell, some other particle has been seated on the periphery. But what is the physics? What is the chemistry behind that one? We have to study that one. See, suppose what we did, how we produce this hybrid copper and silver. We produce at the ice atmosphere. So when you took the ice atmosphere and process that raw piece, then we found that the copper particles becomes a, that means like a core, and the silver becomes like one cell-like structure. Then what is the physics behind it? Then we have to see how the particles, that means they can chance to diffuse during the processing time, and how they will be attached. What is that molecular bonding and atomic bonding, whether that is a metallic bonding or like a passivated bonding, those things we have to study those things. Otherwise, that means we cannot say that how it comes and how it sits on surfaces and where it can be applied. That is also very important part.
Thank
So
you, sir.
why we have studied this silver and copper? Then you can ask me one question, sir. The main important is, suppose you know packaging material, right? Suppose a bread packet. Suppose a bread packet on the surface, if you keep a bread packet, that means a shopkeeper, he purchases the bread packets of almost 50 bread packets he want to sell to the customer. So if he is keeping for at least 5 to 6 days, if customers are not able to take it, some bread packets are subjected to fungi, algae, and he has to return back to the main supplier. Am I right or not?
Yes, sir.
So if you will use those kind of copper, though it is antibacterial property and silver also high antimicrobial property. So if you are just making a core and cell structure, and if you are dispersing those kind of particles on the surface of the packaging material with some variable light carrier, so what is happening is those will help to inhibit the growth of bacteria at a very high rate. so that it can protect the food pump bacteria. There will be the algae formation and the fungi formation will be not be at the, that means fast rate, so it will be subjected to after a long period of time. Like that, it has to be happen. So keeping an application point of view, you have to study these hybrid structures. Yes, sir. Please, any questions, sir? HOD, sir.
Yes, sir. He is okay with it, sir. Dear participants,
Hariom, sir. Hariom, sir.
Sir, very nice, sir. Very informative. So many things is shown.
Any questions,
Very
Hariom,
nice,
sir?
Very nice presentation and showing all setups. Okay, very good, sir.
No, little bit glimpse only I saw, but our Bhargav,
sir.
Dr. Bhargav, that means he worked very extensively in the area of this hybrid machining only.
Yes, sir.
Sir, any of your students are working in the area of numerical modeling, sir?
Yes. So now my two students are working in mathematical numerical. That means mathematical modeling.
Okay, sir.
Of to predict the size of the particles. Already it has been. That means they have. Studied, and also they have submitted the reports, and now we are going to compare with the experimental one.
Okay. Anything on this COMSOL modeling and
No, COMSOL modeling they didn't carry it out. They went through MATLAB, and one fellow Bhargav, he is doing some simulation related to smart material using that lamps.
okay.
You know lamps, no?
Which one, sir?
Lamps. That molecular dynamic simulation.
Yes, sir.
The molecular dynamic simulation, my two BTech students, other two BTech students, they predicted the sizes. And other two BTech students, what happened, they have carried out the molecular dynamic simulation, MDS, using the lamps.
Okay.
So what they did, they took the individual particles, and each individual particle composed of this number of atoms or molecules. Then when it is subjected to different kinds of loadings of a particular size, okay, then how it behaves in a very smart way. First they studied with a single particle, then more than one particle, 2-3 particles, like up to 10 particles they studied.
Okay.
So main important part is, suppose you are changing the temperature or changing some mechanical load. Okay, so how the structure has been changes. That means austenite to martensite to austenite. This structure plays a very important role in a set memory effect. Am I right or not?
Yes, sir. Yes, sir.
And that is to a particular material. So what they are doing, suppose if you are giving this kind of mechanical load upon coating or thermal load, how that behavior will exhibit.
Yes, sir.
So this kind of study they have simulated through MDS.
Okay. Sir, you also mentioned in the presentation that people are working in metamaterials.
Yes.
So whether they're working on generation of metamaterials or
yeah, very good question you asked, Bhargav. But that one, what happened now, I'm revealing. One of my PhD student is working.
Yes, sir.
I will tell you in a very brief way.
Yes, sir. Yes, sir.
See, metamaterials are of various types. And those metamaterials are nothing but only we are engineering the material structure, and that becomes like a synthetic material. Am I right or not?
Yes, sir. Correct.
So those metamaterials, people are working in various ways across the globe. But one of the metamaterial, are getting my point?
Yes, sir.
It exhibits like a set memory effect.
Yes, sir.
So that metamaterial which exhibits set memory effect. Okay, but that metamaterial exhibits set memory effect, it is not available in the market. Please understand.
Yes, sir.
The metamaterial which exhibits set memory effect, that raw piece is not available in the market. First of all, you are engineering the structure of this metamaterial in a very smart way. That bulk form we are studying,
yes,
the various characteristics. Then we are switching over to the metamaterial smart way at a nano level.
Okay, metamaterial to the nano level.
Nano level. That means metamaterials, which is in the form of smart way, for example, set memory metamaterials, it is not available in the market. I am telling you. That means only we have to engineer the structure.
That's what, sir. But we cannot engineer the structure at the nano level, right? So
No. That means we have to engineer the structure at the bulk level. Then bulk work is from that only you have to scale down into nano level, right?
Scale down to nano. Yes, correct.
But
sir.
in the bulk level, where it is available in the market? That is my question.
In the bulk level also, it's not there.
Then we have to
First,
fabricate that one.
Correct, sir.
So when we are fabricating this, what we have to engineer the structure, right, in the bulk form.
So that structure that you are making using 3D printers, sir, or
No, the structure you are making using our vacuum arc melting method.
okay.
You know vacuum arc melting, right?
Yes, sir.
Yeah, by using vacuum arc melting under the innate atmosphere, we are going to engineer the structure. My student Tubin Manuel, he started that work. He
Okay.
made that structure and is going to study the characteristics of in bulk form. Then we'll switch over to the reducing the scale and nanoscale.
Yes, sir.
And where they can be used, that is also one kind of challenging.
Yes,
People have now reviewed, but we want to study. First of all, we want to make it that one at nano. That is the important part. Then we have to go for the application characteristic at physics level.
Yes, sir. That's true. In
It is
shape
newly
memory,
explored. I think so. Across the world, people have not focused on the that means metamaterials at nano level. That is in the form of shape memory.
yes, sir. In form of shape memory, I haven't studied any literature.
Yeah.
People are doing in vibration isolation.
Yes.
That negative stiffness.
Yeah. The negativity and positivity is there. No.
Poison.
Those things people are studying at bulk level.
Yes, sir. True.
But at the nano level, people have not explored these metamaterials in the form of shape memory effect.
Yes, sir. No one has started that. Sir, there is a question in the comment box.
Yes, please, Bhargav.
Sir, any cost-effective method to produce nano gold?
The cost-effective method to produce nano gold. Now, very good question he asked. See, Bhargav, in our method, whatever we have fabricated and you also fabricated, we can able to produce gold nanoparticles. That is not a big issue.
Correct, sir.
We can able to produce conducting and semi-conducting, non-conducting also. Correct? No.
Yes, sir.
But the cost-effective method to produce gold nanoparticles, the question comes, the main is the concentration. So how much amount you can produce per unit time? That is very, very important part.
Yes.
Suppose if you will give me gold, then I can produce some particles. That means the concentration are very, very small. Am I right in our methods?
Yes, sir. Correct.
Suppose if you want to make in a very high yield, at a very cost-effective way, people may go on ball milling. But when you are focusing on the ball milling, the main important problem is we can say the agglomeration. Okay.
Yes.
The agglomeration phenomena. So nowadays, what happened now? Recently, I am telling you 1 month before, I made an MOU, Memorandum of Understanding, along with NITK and one company. That company is a MSME company, it's a startup company under the government of India. Okay.
Yes, sir.
So they have also sister concerns. We made an MOU, NITK Suratkal, and that company made an MOU. And that company now what happened? They are producing the nanoparticles by using a planetary high energy planetary ball mill.
Yes, sir.
Okay, in such a innovative way, make in India concept, they can able to produce the high yield of gold nanoparticles in a very cost effective way in the current scenario. And in turn, 2 months before, I received one call from Belgium, one client of a Fortune 100 company. I received one mail, but I'm not able to meet the requirement. I didn't have time. So they asked me, can you develop a setup to produce nanoparticles in at a very high yield without any agglomeration? So that ball milling currently it is useful. Whatever the technique they have adopted, and that is also copyrighted, Bhargav, for your kind information. I cannot reveal that technique.
Yes, sir. Yes, sir.
Ball milling everybody knows. But the technique, the approach what they made, because now they had tied up with our NITK, that's why they shared some information.
Yes, sir.
We can able to produce those particles at a very high yield, for example, gold nanoparticles, in a very cost effective way, without any agglomeration for a long period of time.
Yes, sir.
In our method also, you can able to produce, but the concentration only, that means it has to peak up. That is only, but we are making it lab scale. When we are going for a pilot scale testing, we have to increase the concentration. We can able to produce gold nanoparticles, not a big issue for us.
Yes, sir.
Any questions?
I think so. There are no more questions, sir.
The concept is how it looks to the audience. Good.
It was too good for us, sir. We were all seeing the presentation from the starting. You started very well with the fundamentals of advanced manufacturing. Then you have taken to
And
nanoscale.
also, what happened, Dr. Bhargav?
Sir.
Nowadays, people are working additive technology followed by subtractive technology. Why not we follow the subtractive technology? We can pursue the subtractive technology followed by additive technology. Nobody across the world people have made.
That's what, sir. This is the first time I'm also
So
listening.
because that this type of concept, my student Praneeth and Umesh and our Dantesh is working, and they have developed that setup, and they are going to another accessories, mechanical accessories. They're going to see develop another system, and already the substrate has been ready, and they are going to start this work.
Yes, sir. This is the first time I'm also listening this.
Yes.
Additive after that subtractive was done, but from
Subtractive followed by additive, I think so. I don't think that many people have explored across the globe.
No, sir. Even I haven't seen any literature in it.
Yeah, that is quite challenging. But now my students they are focusing on that area, and they have also great challenge for them now. Within 1 year, they have to complete that one. They have to show some results. Yeah, Sunil sir, any questions? Bhargav, Sunil Raghuwati.
Hello, Sunil sir.
How they are fabricated, sir?
Sorry,
Nanoparticles, how they fabricated?
who? Sir, who sir? You're asking? Fabricated means that means ourselves or we are fabricating or some company you are asking?
You are doing project now, sir? No, sir.
No, you told na sir, you are adding subtractive to additive. So there, sir, I think so. He's asking how they are manufacturing or synthesizing the
Yeah,
nanoparticles.
that's why I shown that figure. First of all, you have to produce the colloid. So that colloid, how to dispense on the substrate, that is the only important phenomenon. So that we can make a nanoscale patterning on the surface. That is the new work we are exploring now. I've given some kind of glitches or glimpses so that some researchers they can also carry forward.
Yes, sir.
Okay, thank you, sir. Understood, sir. I understood.
Yeah. Hariva sir, no question. Bhargav, what is his name? Our Netranand.
Netra?
Netra is one type of researcher, great researcher is there now.
He's keep on publishing papers here, sir.
But he has to ask questions to me, right? Now it is the time for him to ask me questions. I am the student and he is now one audience.
Sir, good evening, sir.
Good evening, Netra.
How are you, sir?
I am fine by God's grace. How are you, Netranand? Dr. Netranand?
Fine, sir.
Yeah, tell me, Netranand, any questions from your side? I will be happy.
So, what is the method, sir, to increase the mechanical properties of nanoparticles?
What are the methods to improve?
Mechanical properties of nanoparticles.
See, methods to improve the mechanical properties you are telling, right?
Yes, sir.
See, that means methods to improve the mechanical properties of nanoparticles means that only the nanoparticles should be of uniform sizes. If the nanoparticles are of uniform sizes, across the world, there is no such kind of method to produce uniform size nanoparticles. If anybody is producing uniform size nanoparticles, he will get the Nobel Prize. Because due to the diffusion limited growth, we are not able to make uniform size particles. If you are able to make uniform size nanoparticles, then the mechanical properties will be drastically improved. And in addition to that, if you are asking how to improve this, only you have to, if you are scaling down to a great level, then the properties may enhance.
Okay, sir. These nanoparticles can
Suppose
be.
you see, suppose if you are asking like a composite material, how to improve the properties of a composite material wherein the reinforced nanoparticle, then you can say you can play with the size of the particle, you can play with the shape of the particle, we can play with the concentration of the particle, you can play with the dispersion, dispersion of the particles. These things will be there in the matrix. But only nanoparticles to improve its properties means then we have to play with its sizes, uniform distribution, and such kind of method. In our method, we can able to produce the nanoparticles of approximate uniformity of well dispersed, but not a constant sizes which is dispersed throughout the medium. No, we are not able to produce.
So these nanoparticles can apply in biomedical application.
Yes.
So what is the role of this in the biomedical application?
See, for example, one person asked me, one audience asked me gold nanoparticles. Nowadays what happened in immunotherapy, one of the drug which is used to kill the cancer cells, the chemotherapy, which is one of the important drug to kill the deadly cancer cells surrounding the certain location. Okay, so these drugs, in the drugs, some base fluid is there, wherein some gold nanoparticles are incorporated or dispersed. The main important part. Some people are also using silver nanoparticles. Why I am telling you, when these gold nanoparticles are dispersed in a liquid drug and they are injecting into the bloodstream, if a person is subjected to some kind of carcinoma and it has been located in a certain organ, how that means the chemotherapy followed by the high therapy, immunotherapy and targeted therapy they are killing, because those gold particles have high plasmonic resonance property. So when you are just injecting into the bloodstream, which organ that has been subjected, what happens? They start to kill those cancer cells surrounding this organ first of all. Why? Because they will be high plasmonic resonance. They will generate more amount of intense heat. Though have large surface area to volume ratio, are getting my point, or high surface free energy, those intense heat will not be able to cope up by the deadly cancer cells. That's why whatever people are using these gold nanoparticles or silver nanoparticles in biomedical, in specific drug delivery applications to kill the cancer cells. And now people are using in immunotherapy, in chemotherapy, as well as in targeted therapy. In biomedical, one of the applications. Then if you say nitinol nanoparticles, now whatever you're going to do are produced by using our method, which is acting as a safe memory alloy based nanoparticle. That is nitinol in a bulk form, it is safe memory alloy, which has a safe memory effect. It may be like we can say one way, two way, or superrespiratory behavior also will be there. But that nitinol's material is used in, that means bioimplants. But at nano level, people have not explored so far. That means we are focusing on some kind of automobile applications in the current scenario and some sensors. And in other biomedical, you are telling, suppose food, to protect the food from bacteria, people are using usually now copper nanoparticles. By using some kind of carrier agent, people are using some vermiculite carrier. So they are dispersing those particles so that it inhibit or it reduce the growth of bacteria. As a result, the reliability of those food packets or food will be more. You understood, Netrana?
Yes, sir. So another question, sir.
Yeah.
Sir, during the production nanoparticles, any effect of grain size and crystallography orientation?
Any?
Grain size and crystallography orientation.
Yes, obviously. Why? Because in our case, it will change because the grain size, you see, for a bulk metal, when you are taking, and we are going through melting and evaporation phenomena, when the nucleation starts to take place, obviously the grain orientation and grain size changes. Are you getting my point or not?
Yes, sir.
Yeah, obviously, because in our phenomena, it is nothing but one heat treatment operation we are doing, where you are melting it, and from the molten pool, where it has been ejecting, and it is going towards or approaching towards the nucleation. Obviously, the orientation changes, the grain size will be also changes. But when we are able to control that grain sizes by tuning the parameters and surrounding medium, based on the trial and error, we can able to get different properties of the material.
So if the grain size and that crystallography will change, sir, that mechanical property also change, sir.
Which one?
Mechanical property means the density, hardness, it will change, sir.
But density, hardness, if you will change is how? At a nano level. So at a nano level, the mechanical hardness, how can you change it nano level for one single particle? For a single particle, if I am changing the grain size, if I am changing the crystal structure, so for a single particle at molecular or atomic level, not in the bulk form, so how the mechanical property like hardness will be changed for that one? Which kind of test you have to go for that one? That is my concern. We cannot go for such kind of tests are not available. Okay. Even though if powder is there, okay, so if you're going to check the hardness of the powders, even though you do go for some compacts and other kind of things, am I right or not?
Yes, sir.
So if you say a single particle is there in a powder, millions of particles is there. The single particle, if you will take, how you will check its hardness? There is no such kind of equipment available in the world.
Okay.
Correct? No.
Yes, sir. Yes.
Mechanical properties. How can you see means in a bulk powder form, not in a single particle sizes. When you take in a bulk powder form, wherein the particles are of very small sizes, there you can play with the mechanical properties.
Okay.
But bulk powder form, that is also very difficult. You have to go through compaction and you have to make it like a solidus material. People are telling nano indentation. Nano indentation means what? You are indenting at a nano level, but a single particles, if it is full of powder,
Yes, sir. Yes, I understood, sir. Now.
yeah. Why? Because its mechanical properties, obviously you can change it, but for testing purpose, that equipment is required, right?
Yes, sir. Yes.
Very difficult. Only if you are making, but what happened? No, if you are making a uniform size particles, and you are taking in a bulk form of the powder particles, then you can say this property will be greatly enhanced. But when you are speaking about this structure and the grains orientation and the grain structure, that is also plays a very important role. For testing purpose in a bulk form is very difficult. In elemental form, again you have to go through in a bulk form only. But bulk form is what is happening. Again you have to go for compaction. Again heat treatment to sintering.
Yes, sir. Yes.
Correct? No.
Yes, sir.
But I don't know, Bhargav, anything is there in a powder form, you can check the hardness. People are telling the most hardness, that means from the powder particles also you can able to check it. I think so in a bulk form only they are checking.
No, sir. They're checking at the bulk form only.
Huh?
In powder form, it's not available.
No, how you can test it? Even though if you are taking a powder of 20, in the powder, let us say 100 particles are there, how can you check the hardness part? Very difficult.
No, it's not possible, sir. But what Netra is asking is theoretically, if we say that grain structure as well as this.
No, if the grain structure, see, suppose if in a particle, let us say of 10 nanometer size particle is there.
Yes, sir.
So if you want to change the grain structure, that 10 nanometer particle consists of number of grains. Am I right?
Correct, sir.
They are oriented in different directions.
Yes.
So if you want to take the 10 nanometer particle, let us say you are making the grain size small. So if the grain size is small, then it can have a high strength. Am I right or not?
Correct, sir.
And also people are telling if the grain size is small, then it will have a large surface area to boundary ratio. So it will impede the dislocation. Then what happens? Its strain hardening also takes place. So we are going for mechanical testings.
Yes,
Plastically deforming it. Or also its strength increases.
yes.
But how to test that one?
No, we cannot test it, sir.
That is the phenomena. If you take in a particle form or in a bulk form, the same kind of phenomena will occur, right? If you are changing the grain structure. But our main aim is that means how to improve the mechanical properties of a powder particles means the main important is you have to make a uniform sizes.
Yes, correct.
Uniforms, until and unless uniform sizes are there, then if you are taking in a powder form, that mechanical will be behaviorally changes. Or else again you have to go for the compaction, same thing only, right?
Yeah, the process is same, sir. If you want to
But
test it, then you have to
theoretically,
go.
you cannot prove. Theoretically, everybody knows that because reducing the grain size and its strength will be increases. Then the strain hardening effect will be more. Am I right or not?
Yes, sir.
But strain hardening effect, how will do? Until unless you have to go for cold working condition. Or else some method may be there. Suppose you are just dispersing the particle like coating. What Netrananda worked. If you are going for coating application, in that coating, the slurry, whatever you are making, or thermal spray, whatever it is there, if you are coating the particles on the substrate, and you are applying some kind of hardness testing, or hardness, you are going for hardness test, but only it comes in, we cannot say the particle will be only indented. Okay, how can you indent the particle? Whether that the indenter, that means it is much more smaller than the particle size. It can indent across the whole that surface along with the substrate, right?
Yes, sir.
So individual particles you cannot able to indent. Why? Because it is small sizes.
Yes,
That kind of small indenter very available.
Yes, sir.
You are telling nano indenter. Whether nano indenter can able to indent a nanoparticle?
No, it's not possible, sir. That's not there.
So the methods are not available.
Yeah.
But if you see in a very physics point of view, that is obvious. It is obvious that we can change the mechanical properties by changing the grain size. But if you change the grain size, ultimately again we go to bulk form only.
Yes, sir. Yes, sir.
Suppose somebody asks me, how can you go a tensile testing for this particle? What is the UTS for that particle you are obtaining?
Hmm.
See, Bhargav, suppose a bulk material I am giving you steel. You know this when you are applying a steel, that means a tensile load unidirectional, then you can calculate its yield strength and UTS. Am I right or not?
Yes, sir.
Suppose if you are just scaling down the steel in the form of nanoparticle,
Yes, sir.
then how can you calculate the tensile strength of this particle? Even though that means you reduce to scale, its mechanical properties greatly enhanced. People are telling.
Yes, sir.
And also we are also able to, that means able to quote it in various literatures.
Hmm.
Suppose we are reducing it to nano level, then what is happening? How you can say its UTS is this much only?
Yes, sir. That's difficult.
Why? Because whatever the steel is there also grain structure and the grain size. We are reducing it to nanoparticle in our case by using heat treatment process, like melting and evaporation. Obviously, the grain size and structure may be changes. How can you ensure that UTS will be same in the bulk and in the nanoform are same, even though it is a homogeneous structure?
Hmm.
It is a homogeneous composition also, you cannot ensure, right? You will be going to nano level.
Yes, sir. Yes, sir. Correct.
Nityanand,
Yes, sir. Yes, sir.
you understood,
Yes,
eh?
sir. Yes, sir.
Yes. Yes, sir. Yes, sir.
Then any other questions, Bhargav? Very good discussions, Bhargav.
Yes, sir. Yes, sir. I think so. No more questions, sir.
Babu?
Good evening, sir.
Hello?
Good evening, sir.
Who is speaking? Babu? Babu, eh?
Sir, my voice is audible, sir.
Yes, yes,
Hello?
sir. You are audible, sir. Yes.
Yes.
Sir,
Please.
thank you for the wonderful session, sir.
Thank you, sir.
Sir, I want to ask one question.
Yeah, please.
Sir, I am doing research on biodiesel, sir.
You are working on biodiesel, okay?
Yes, sir. Suppose I want to add hybrid nanoparticles, like two different nanoparticles in biodiesels. What is your comment on this one, sir? Can I proceed?
Two different nanoparticles means you are taking a hybrid in the form of core cell or different nanoparticle dispersed in a biodiesel?
I combine, sir. For example, some percentage one nanoparticle and some other nanoparticle.
That means you are telling that two different types of nanoparticles of elemental, not hybrid. That means two different nanoparticles dispersing in a biodiesel. Am I right?
Yes, sir. Yes, sir.
Then from that, what you want to study?
I want to test the engine performance, sir.
Engine performance.
After doping the nanoparticles in biodiesel.
Can you tell me any example of a nanoparticle? Which type of
For example,
nanoparticle?
TiO2, Al2O3.
Okay, TiO2,
Titanium oxide, aluminum oxide, sir.
Okay.
For example, I want to add in a biodiesel after doping with ultrasonication process. So I want to test the engine biodiesel properties, like engine properties. So whatever breakdown efficiency, brake specific fuel consumption, like that. Can I proceed, sir? Is there any?
Yeah, you can proceed it. That I am not denying you, but you have to see some literatures. Then whether people are using this more than one kind of that means nanoparticles are dispersing in a biodiesel, and they are studying what kind of observation they made. Whether the chemistry and physics is meeting the requirement, we don't know these things. Why? Because those who are going for application in biodiesel, they can able to study those things. But two different types of nanoparticles, if you are dispersing in a biodiesel, that means in a diesel, then you are studying the effect of these particles on the engine performance. You can able to study.
Okay, sir.
But we don't know how it behaves. What are the things you study? What are the output? What you want to study? Whether the outputs, these particles, properties you have to see. Based on this kind of all compatibility only, you have to use another.
Like to reduce the exhaust emissions.
See, the titanium dioxide, that means it is oxide content. The aluminum oxide content is there. But the titanium, what happens? Low thermal conductivity. These things we have to see, all those things.
Okay, sir. Okay, sir. Thank you, sir.
Okay, you are welcome.
Thank you, sir.
So, Bhargav,
Okay, sir. So, thank you very
can you
much.
wind up now?
Yes, sir. Yes, sir. Thank you very much for your enlightening session, sir. Actually, you have given so much of insights towards nanoparticles, and there is a lot of research scope in this.
Yes, yes.
So I hope with this session, many people would work towards synthesis of nanoparticles as well. What Netra has asked, maybe there's a scope towards mechanical properties of nanoparticles.
Mechanical properties. Then we have to see that one.
Yes, sir. Yes,
Good
sir.
question. But this question has been asked in NIT Allahabad, one professor. But that kind of scope, what happened required, scope is not available till today.
Yeah, true, sir. So we will be having more such interactions in near future, sir. So thank
Sure,
you for
Bhargav,
attending,
sure.
sir. Thank you for attending. Thank you for gracing this occasion.
Yeah, thank you very much, Bhargav, for your kind invitation to me, and also thankful to all my audience who are presented in this platform. And also, I express my heartfelt thanks to your management and one of my senior colleague Haribabu sir and my former student, Dr. Netra, and my dear, my closely hearted Bhargav.
Thank you, sir.
Okay, shall we now leave now, Bhargav?
Sir, good night, sir.
Good night, Haribabu sir. Is not
Very,
asking Bhargav anything.
very interactive, sir. Session is very interactive.
Huh?
Okay,
Thank you,
sir.
Haribabu sir.
Thank you, sir. We will wind the session. Thank you.
Yes.
Thanks a lot, sir.
Thank you.